Good evening, everybody. Welcome to Slooh. You are joining Paige Godfrey. I am here with my Intro to Astro course, and tonight we are going to talk about higher dimensions. And I called the live cast Higher Dimensional Thinking because I think that we are specifically talking about higher dimensions, but we're also talking about a different way of thinking about the universe and the consequences of what it means to live in a universe. If you're following along with me at slooh.com, I have a screen share up because I actually gave a presentation on this back when I was in college, and I'm going to use that tonight to guide our lesson. So I also should warn that if you followed me last week, you heard that I was using my husband's laptop because mine was kicking the bucket, but I brought it to the Apple Genius Bar and they found nothing wrong and it hasn't been acting up since. So we're taking a stab at using my laptop again tonight, and hopefully it doesn't cut out on me. And if it does, I promise that I will get back online as quickly as possible. But knock on wood, I don't want to jinx myself, but it hasn't cut out in 2 days. So we'll see. All right, so let me share this with you. And let's get started talking. So we know that we live in what we call the observable universe. Sorry, it's okay. My computer's fine. We live in what we call the observable universe. And what that means is we know that our universe it could be actually finite or infinite. We don't know. But what we do know is that the light that we see, that we're able to take with our telescopes, to look at with our eyes, has been around since the Big Bang, since about 13.8 billion years ago. Anything beyond that, the light was not there. The light was not there to travel around the universe. And so therefore, everything we see is called the observable universe, because perhaps there was universe that existed outside of when this light appeared for us from what we call the Big Bang. Now, a lot of this we're going to talk about tonight is going to get really abstract, so bear with me. I'm definitely not an expert at explaining it. Most of it is really hard for me to even sort of comprehend myself, but we'll get through it. It's a fun topic, I think. I like to think outside the box like this. So there's many theories cosmologists have come up with for potential ways to describe our universe and where it lives, if it lives in anything that is larger than itself. And a lot of them sometimes are not taken very seriously. Sometimes they don't have really any sound scientific proof, and other times they have a lot of sound scientific proof. But it's one of those things that how will we ever know? How will we ever be able to prove any of this? But I'm going to run through the top 5 types of universes that might exist. We call this the multiverse. So the multiverse theory is that there is not just one universe, not just our universe, but many universes. And the Big Bang was just the start of our observable universe, and that there exists outside of that other universes. And so there's different ways that these other universes can exist. And the first one is called infinite universes. So space-time, the 3 dimensions of space and the 4th dimension of time, this fabric that we've talked about for the past couple weeks, the shape of it is most likely flat. I know this is a really weird thing to think about, but space-time could be spherical or even donut-shaped. And what's hard to comprehend about this is space-time is 4-dimensional, 3 spatial dimensions. And so how am I calling it flat? Your brain is going to have trouble with trying to image this, if it even can. Like, I'm not your brain specifically, but brains in general might not be capable of actually picturing this. But space-time can have a shape to it. And what it would mean if it was spherical is that when you travel around space-time, you eventually get back to where you started from. Like if you were to travel, pretend you're an ant on a basketball and you start at the top and you travel all the way around to the other side. That's sort of what we're talking about here. But it seems like space-time is flat. But if space-time then just goes on forever, if it's infinite, it has to start repeating at some point, because mathematics says that there's a finite number of ways that particles can be arranged in space and time. So In order for our universe to be infinite, it must repeat eventually. So that if you look far enough in any one direction, you should encounter a repetition of our observable universe, another version of us, of you, of me. Infinite versions. So some of these versions could be us all sitting here doing exactly what we're doing right now, or it could be something completely different from what we're doing right now. But because the observable universe extends only as far as light has had this chance to go in the 13.8 billion years, the space-time beyond that 13.8 billion light year distance can be considered its own separate universe. So in this way, all of these multiverses exist sort of next to each other in kind of like a patchwork quilt of multi-dimensional space. Really, really abstract. This isn't even the most abstract one. Let's keep going. The next one is called the bubble universe. So this says that our universes, the multiverse, could have arose from eternal inflation. Inflation is where the universe expanded rapidly after the Big Bang as we know it, kind of like when you inflate a balloon. Eternal inflation suggests that some pockets of space-time stop inflating, but others continue to inflate forever. And then this would create isolated bubble universes. So our own observable universe, where inflation has since ended, allowing the stars and galaxies to form. So this is an expansion, so don't confuse inflation with expansion. Our universe is expanding. That's something we're going to talk about next week. But inflation was this time period right after the Big Bang before the stars and the matter started to coalesce together into stars and galaxies, and gravity took over. But our observable universe is just a small bubble in a vast space of some other bubble universes. Some are still inflating. Some might have stopped inflating like us. And in this space of bubble universes, the laws of physics might be different than ours. Maybe each universe has its own laws of physics. So one of the really interesting things about our universe is that we know, well, classical mechanics and quantum mechanics, yes, they don't agree at large scales and small scales, and we definitely don't have the laws of physics down pat, but we know that our universe is very finely tuned to work with our specific laws of physics. That doesn't mean that that's the only way a universe could work. There could be other sets of laws of physics that allow for a very different type of universe. The third type of universe we'll talk about is a daughter universe. So in quantum mechanics, which is the study of subatomic particles, really, really small particles, suggests that multiple universes could arise from probabilities. So quantum mechanics is a way of describing the world based on probabilities instead of based on specific outcomes. So there's a lot of math behind quantum mechanics. It's definitely one of the courses in college that I did not do well in. We'll just start right there. And the mathematics of this daughter universe theory suggests that all possible outcomes of any situation do happen in their own separate universes. So today I drove to the gym and I had a choice when I left my street of turning right or left. In my universe, I turned left, but I, in another universe, would have turned right because all possible outcomes of every situation occur. This might be the most abstract theory to me, because every single thing, person, animal in the whole wide world has, just our planet, just Earth, has so many different crossroads every 2 seconds of the day. How could there possibly be a universe for every single possible outcome of a situation? My brain cannot wrap around the statistics, but this is one of the suggestions that quantum mechanics presents. And we call these different little possible outcome universes daughter universes. The next one is another mathematical sort of universe. So for a long time, mathematics has been considered a tool that describes our universe. The laws of physics, mathematics, it describes our universe based on the way we see it. If we were not here to see it, Would mathematics exist? It's like that tree falls in the forest. If no one's there to hear it, does it make a sound? We know that the tree would ripple the sound waves, but if there's no ear to process the sound waves, does it make a sound? So if we're not here to observe the laws of physics and mathematics, do they exist without us? Or is math itself a fundamental reality, and our observations of it are just a perception of this absolute mathematical nature? If that's the case, then perhaps our particular mathematical structure that makes up our personal universe is not the only option. Like we said earlier, there could be other universes that follow different sets of mathematic laws, and they would exist in their own separate universes. So a scientist at MIT, Max Tegmark, proposed this idea, and he describes it as a mathematical structure is something that you can describe in a way that's completely independent of human baggage. He really believes that there is this universe out there that can exist independently of him, that would continue to exist even if there were no humans. And the fifth theory, the one that we're going to talk about in way more extensive detail with my slideshow that I have prepared, is parallel universes. So this arises from string theory, and it's also called Brane worlds. So the idea is that our four-dimensional space-time that we know is just one brane world, one brane. And there could be many more dimensions to our world, up to, I think, 10 is the most favorite answer, but I believe that there's been theories that go up into the 20s for how many dimensions we might have. So other three-dimensional branes might float around in this higher dimensional space, creating a brane world. Okay, so let's dive in on this one. Let's just dig a rabbit hole and keep going. So when I had given this talk to my cosmology class, I titled it Black Holes as Universes, because this brane world theory, one of the things I had researched was maybe black holes are all individual universes. But that's not, we don't need to be that specific when we talk about this. I'm going to give a lot of background. But first, we can just look at this comic that I thought was hilarious when I made this presentation. String theory summarized. Person 1 says to person 2, I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. Person 2 says, okay, what would that imply? Person 1 says, I don't know. Isn't that just, I mean, that's just astronomy right there for you, right? So of course I had an objective slide. We don't need to go through that. You're stuck with me till the end anyway. So, okay, extra dimensions. Ugh. How can we even get our brains to imagine this? We can't see them. Why can't we see them? There's something called flatland, and this is an analogy that helps us to try to understand multidimensional space. If you pretend that there is a two-dimensional person, so if you were flat, you would be two-dimensional. You would just go, you would have a height and a width. You would not have a depth. And two-dimensional people cannot experience three-dimensional space, because three-dimensional space would look like cross-sections. So if we focus on this image here, which is a little bit dark, so bear with me, but this plane, this square, is flatland. Now, if you were a person on flatland, you would not be standing up out of flatland. You would not have this third z dimension. You would just be laying flat on flatland. You would have two dimensions. Now, if a three-dimensional object tried to cross through flatland, like this sphere, you would only be able to see it cross-section by cross-section. It's too hard to picture 4 dimensions of space, so instead we use these analogies of being 1 and 2-dimensional to try to help us picture it. So another analogy is an ant confined to the surface of a garden hose. This is an example where the ant, from close up, thinks it has 2 dimensions. It can go long ways down the garden hose, and it can go around the garden hose. if you were really far away, you're a mile away from this garden hose, it looks to you to actually be one-dimensional. Because if you're standing like here, you see the ant on the garden hose and it looks 2D, but then, this is one dimension and then this is another dimension. From really far away, you only see this one long dimension. So if you're a large three-dimensional observer, you can't see this third and second dimension even depending on your distance. So it's just, so extra dimensions, multiple dimensions they're not a visual effect, but our perception of them is heavily affected by our visual limitations, if that helps to explain it. Okay, let's keep going. Another really good example of this is a hologram. A hologram, if you've ever played with one, projects a 3D image onto a 2D surface, but still recovers all 3D information. I have to tell you, I was in my senior year of undergrad at the College of New Jersey, and I took an optics course. And for one of our labs that we had to do at the end of the year was create a hologram. We got to bring in whatever object we wanted, and we set up this laser system that created the 3D light onto the holographic surface. It was the coolest thing I think I've ever done. It was probably the coolest experiment I ever did in 9 years of college. 4 undergrad, 5 grad school. But yeah, it was amazing. Anyway, so when you pick up a hologram, it might be hard to tell from this picture, but it's just a 2-dimensional, it's like a piece of paper, essentially. It's like if you were holding a piece of paper. The image is just imprinted on the surface. The image is printed in 2-dimensional space, but it recovers all 3D information. You can kind of turn it around and see the depth of the objects that are printed on this image. So imagine that pretend our universe is a 3-dimensional projection. When we talk about this, we're ignoring time as a dimension. We're just talking about spatial dimensions. So imagine our universe is a 3-spatial dimension projection of a higher dimensional space. So when you project this 3D cube onto a flat surface, it is 2D, the projection is 2D, but the actual object was 3D. So what if we are a 3D projection of an actual universe that has more dimensions than just 3? Crazy. Okay, so maybe I've convinced you that it's possible to have other spatial dimensions. What could they be? Well, some of them are tiny curved dimensions, potentially. So if you imagine a ring, and then this is 1-dimensional. Now you have, or 2-dimensional, sorry, up and across. Now you have a 3-dimensional when you add a bunch of rings. So you have this cylinder. Now if you have multiple cylinders and you start to fill in the rings like donuts, you can start to kind of, this still looks, well, to you, this is a screen, so this is 2D. But you can see the recovered 3-dimensional depth here. But this is a way to sort of build extra dimensions, and they could kind of be like tiny curved up rings. There could also be large dimensions, larger than ours. So this is a 3D cube, 3-dimensional cube. It has a height, it has a width, and it has a depth, or X, Y, and Z. If you pretended you made this cube out of paper, like origami style, this is what it would lay out like, all of the pieces. So if you fold this down and then wrap this around, you'd recover your cube. If this is confusing, then draw this on a piece of paper, cut it out, and bend it, and you'll be able to see that you just made a cube. Okay, so a 4-spatial dimension this is a disaster, and it's really hard to try to understand what this looks like, but if you pulled it all apart in the way that we pulled our cube apart, this is what it would look like. Yeah, so making a 3-dimensional cube into 2 dimensions looks like this. Making a 4-dimensional cube thing, I don't know what it's called, it's not a cube, into lesser 3 dimensions would look like this. So then what's a brane? A brane is a membrane of space that is manifested in a bulk of space and confines particles and forces on it. The bulk is the higher dimensional space, and it contains the branes, and it can allow travel of some particles in between branes. So if we look at this depiction here, our brane is this sort of plane in this higher dimensional cube. Now remember, we can't visually imagine dimensions more than 3, so we're dumbing this down into 2D branes and 3D bulk, whereas in reality, we know that our brane would be 3D and the bulk would be 4, 5, 6, 10D. String theory has 3 different types of strings. So when the smallest particles in the universe, way back when, used to be atoms. Then we found neutrons, electrons, protons. Great. Well, now we're all the way down to quarks and leptons. But string theory says that there's something even smaller than those called strings, and they're little vibrating strings. And it has 3 types of strings: closed loops, loops where both ends attach to the same brane, kind of like a prominence on the sun, where the flare like comes up and then reattaches down on the other side, or strings where each end attaches to different branes. Closed loops are the gravitons that travel through the bulk. Each attached end of a vibrating or oscillating loop is a particle in our universe with a force that it provides. So every time a string is attached to our brane, we see it as a particle. So in this graphic here, we're kind of looking at a spatial slice of space-time. So if we have these branes, you can see some closed string loops, some that connect across different branes, and some that connect on their own brane, and you can see the dots at the end of the loops, or the strings, are representing the particles in that brane or universe. This is getting pretty intense. Okay, so if we lived in a brane world, if we have one brane could be the weak brane, so you know that we have different forces, and we have these fundamental forces in our universe. One of them is the weak force, one of them is the strong force, and this helps to explain the hierarchy problem with these forces. So if gravity travels through the bulk and across, like, so in between branes, gravity travels like here. Remember we said way earlier that the branes can allow travel of few particles in between, which are gravitons. So the strings that connect 2 branes together would carry the force of gravity. So if gravity traveled across the bulk and across dimensions, it would explain why gravity is so much a weaker force than the other 3 fundamental forces in our universe. Because the 3 other fundamental forces are confined to our universe, whereas gravity is traveling between other universes. Okay, so great, our universe is a brane, and it maybe connects to other branes in this higher, maybe 10D, like 10-dimensional brane world bulk. So would we ever, what are we looking at? What are we thinking of when we try to look around our universe and potentially see the connections to another brane? Potentially black holes. The idea is that every black hole is a new universe. So it would be an effect from the spin that particles have. Imagine space-time not as 2D, but let's go all the way down to a 1-dimensional rod. Bending the rod corresponds to curving space-time. Twisting the rod, so pretend pretend you have like a string or like a rope, and you bend it into a circle, you just curved space-time. Well, if you twisted the rope, That's called torsion. In extreme environments like this, space-time torsion would manifest itself as a repulsive force that counters the attractive force of gravity coming from the space-time curvature. So our universe, something we're going to talk about more next week, is that our universe is expanding, but it's actually expanding at an accelerating rate. This is possible with this torsion of space-time idea. The motion of matter through a black hole's boundary, the event horizon, whereas after it goes past the event horizon, we can no longer see it, would only happen in one direction, providing a direction of time that we perceive as moving forward. The arrow of time in our universe would therefore be inherited through torsion from the parent universe. Think on that for a second. So our fourth dimension of time, if this string theory, Brane world theory was right, our dimension of time that only moves in one direction would be a byproduct of having a parent universe that connected through torsion of our space-time. So one of the things that is being tested for this is the Large Hadron Collider is going to test for microscopic black holes. I made this presentation in 2013, and so I haven't done updated research to see if they've done this or not. But if you smash two protons together, it should not result in a microscopic black hole unless gravity is actually stronger than we think. So black holes are created when there is a supermassive singularity. So for example, when a star that is much more massive than our sun goes supernova, after it's blasted off its outer layers, the core is so dense it can collapse under gravitational pressure from its own weight into a black hole. So if you smash two protons together, you might be able to get a gravitational collapse that is strong enough to create a microscopic black hole, but only if gravity is actually stronger than we think, because if it's not, then science says that this can't happen. All of the energy would be concentrated into the tiny area, and this microscopic black hole, which would only last for like a microsecond, it's very fleeting, would be detected by the burst of particles around it outside the event horizon of it. So it should take more energy than the Large Hadron Collider can produce by smashing the two protons together. But if stronger gravity existed, it would make the energy threshold attainable to be done. Wow. So my last slide for the class was another comic, but I must say that reading it back again, it's not as funny as I thought, but you could go ahead and read it if you'd like. But I also have my references listed here, and they're really good. So Lisa Randall is a very famous and very intelligent cosmologist that works on string theory, and she's written books, she's given talks, she's done a lot. So if you are interested in reading more about this sort of thing, she's definitely a name that you should look for. Another name that I highly suggest is Ethan Siegel. He is an astronomer. I've met him several times at the American Astronomical Society conferences. He's wonderful. And he has a blog called Starts with a Bang. And you can follow him on Twitter. And he writes a lot about cosmology and things like this. So these are my other references as well, if you were interested in looking up more information on all of this. But there was a lot. It's a lot of really abstract thinking. I know right now that I did not fully explain everything that well, and that you might be leaving this more confused than you were when you came in. Don't worry, I am too. So it's definitely very abstract. It's really hard to wrap your brain around this kind of idea when you can't visually imagine it. So when we can't imagine and visualize multiple dimensions beyond three spatial dimensions, it's a really hard task to do. There's a lot of mathematics involved, and props to the cosmologists out there. We appreciate you. So I hope that I've entertained you at least, if not confused the heck out of you. But I will leave it here for the night because that's a lot to soak up. And you can go, try to think on this for a while, and maybe we can get a nice discussion going on the discussion boards about this sort of topic. But next week, I'll be back and we'll be talking about our accelerating expanding universe with regards to dark energy. And we'll also talk about dark matter and how we know that dark energy and dark matter both exist, what they are, and how do we know that they exist when we can't see them. So that is a topic that is a little bit abstract because, again, it's something that you cannot see, but there is scientific proof of their existence. And so I can at least give you that next week. It's a little bit more concrete. Well, I hope you've enjoyed tonight. I hope you have a great week. I believe next week I'm going to have to move the show again. I will be returning from our NSF conference on Wednesday night, so I might need to have the show Thursday night. So I apologize for all the schedule changes, but I appreciate your flexibility. And as always, you can find the live cast in our past live casts should you have missed it. So in the meantime, if you caught earlier, Paul Cox had a live cast introduction to the Messier Marathon that we're going to be having this Saturday. And if you missed it, you definitely want to go check out what he talked about and how to get prepared for the Messier Marathon. And then on Saturday, if you celebrate St. Paddy's Day, and it's a great time to get involved with this Messier Marathon. I've been told that there might be some hints of some green aurorae being shown, and nebulae. I don't know why I said aurorae. It's late. I'm tired. Green nebulae through the our Slooh telescopes, and so please join us on Saturday for this really exciting event. It doesn't come around that often, so enjoy it while you can. Have a good night, everybody. Clear skies.